Hey guys, it's Ron. Thanks for joining me again for another lab. Hope you're getting something out of them. Lab 9 left off with configuring RIP and RIP v2. Here we're going to get into EIGRP. All right. So EIGRP is another distance vector routing protocol. However, most people consider it a hybrid protocol because it has characteristics of both a distance vector and a link state. All right. Specifically, for the distance vector side, when I'm building what EIGRP considers a neighbor relationship with somebody, I'm going to send my entire routing table to them. All right. I'm just going to dump it on them. Right. Now, once the network is considered converged, meaning every router has shared all of its network with the people it needs to talk to, EIGRP is going to kind of shut down that whole sending updates. All right, RIP continued to send them every like 30 seconds, just pounding your network with these updates. Well, EIGRP needs to be able to scale, for a really large network. So sending those updates, that often, it's just going to kill your network. So what it does instead is it switches over to being more like a link state algorithm, where I'm only going to send updates if an actual network change occurs. If a link goes down or we add another router to the mix, something along that lines, something is going to have to change in order for me to send an update to somebody. And instead, I'm just going to periodically send these hellos. And these hellos are going to let my neighbor routers know that, hey, I'm still alive. And I'm going to receive hellos from other people. And, that's how I know that they're still alive. Well, these hellos are really small. They're not these huge routing tables that would happen if I had to send them out every 30 seconds for a large network. All right, so that's where we kind of get into the play of, oh, this is more of a hybrid, algorithm or protocol. So a couple more specifics about EIGRP before we get into actual configuration is administrative distance of 90. So it's slightly less than the 110 that we saw for RIP, which means it's going to take priority. Also, we're going to get into this thing called autonomous systems. Okay, through this autonomous system number, we're going to be able to kind of determine the scope of our network. Meaning, all of these routers that have this autonomous system number are going to share routing tables. They're going to share updates, stuff like that. If somebody else has a different autonomous system number, we're not going to share it with them. So we're kind of breaking up, segmenting our network. Okay. Now, a router can have multiple ASs assigned to it, which is going to allow us to merge our network with maybe somebody else's network, and then we'll just take care of a little bit of redistribution from one autonomous system number to the next. All right. In this case, I'm just going to use one AS. Now, when we did a show IP route from the RIP side of the house, our RIP routes were identified by R's. In EIGRP, they're going to be identified as D's. And you'll see that here in a bit. And that's because EIGRP uses what's called a diffusing update algorithm. All right? And that's what, happens in the background to ensure that the network converges very quickly, and it does so in a non-looping manner. Also, another change to EIGRP is when we left off with RIP v2, we were talking about, we're gonna use multicast instead of broadcast because it's more efficient on the network. Well, EIGRP takes it to another step and uses RTP, which is the Reliable Transport Protocol. So it's going to use multicasts. It's going to use 224.0.0.10. But there's a minor tweak to it. It's going to send these multicasts out when it needs to send updates, and it's going to expect that its neighbors acknowledge that they received it. Okay, and that if EIGRP doesn't receive that acknowledgement, it's going to switch over to unicast, and it's going to send that update specifically, directly to that neighbor. And if it again does not receive an acknowledgement for like 16 tries, it's going to determine that, that router's dead. So just another mechanism for making sure that those updates are getting out there, but they're doing it reliably. All right. Another thing, when we did RIP, we talked about hop count as the only metric for determining what's the best route somewhere. And we noticed that that wasn't an efficient way of doing things. EIGRP by default is going to use delay, and it's going to use bandwidth. All right, bandwidth and delay. All right. Now there are other values that we can use, like MTU size, load, but in order to do that, we end up modifying what's called K values, and unless you're really smart on the algorithms that EIGRP uses, I don't recommend you making those changes, because you can negatively impact the routing on your network if those values are screwed up. Plus, if you modify those values on your router, those values have to match on every other router that you're going to send those updates to. So it's just an extra layer of work that you're adding to yourself. And bandwidth and delay does a pretty good job in most networks. All right. So another thing worth noting is there's this thing called max hops. Okay. In the RIP world, we use this max hop to determine if a network was more than 15 hops away, it's unreachable. Well, in the EIGRP world, we use it in a different manner. This is more for on the network discovery side of finding, different neighbors. When we send these updates out, they're going to go this many hops, right? So that kind of determines the size of our network, how far away these updates can go. By default, it's 100, but you can change it to 255. All right. So as you can see, it's going to scale a whole lot bigger than RIP ever could. And lastly, there's this thing called PDUs, Protocol Data Units. It's what's going to allow us to, route for IP, IPX, AppleTalk. We end up forming tables for each one of them. But really, in the real world, IP's king, so you're pretty much only going to see IP stuff. So I'm not even going to get into that. All right, so let's go ahead and get into it. We're going to start with router B. I'm going to bring up command line interface, enable config T router EIGRP, and here's where we're going to specify the autonomous system number. So I'm just going to choose a number between 1 and 65,535. I just have to make sure that number is going to match in each of my other routers. I'm going to turn off auto summary. Then I'm going to specify my network. And here, again, I'm not specifying the network itself. I'm specifying the interface. All right. So the network hanging off of that interface is what's going to end up getting used. So I could break it all the way down to that specific interface, or in this case, 192.168.0.0, I'm just going to specify the classful address, kind of like we did in RIP. All right. So that should identify my serial 00 interface as well as my serial 01 interface. All right. Here, though, 172.16. Now, ordinarily, because this is a class B, I would be just doing 172.16.0.0. But in this case, I want to actually break it down, right? So I know the network that's hanging off of there has the 1.0 network attached to it, right? So I'm going to specify 1.0, and I'm going to do another question mark. Notice there's an EIGRP wildcard bit. What this is the opposite of a network mask. A network mask identifies the network. The wildcard bits identify the host. So it's the opposite. So we can take 255.255.255.255 and just subtract our net mask, and what we'll be left with is just those host bits. Or I can take my block size and subtract 1. So in my case, I have a /26, which is a 192. So 255 minus 192 is 63. So I can go 0.0.0.63, and that works just fine. Now, slash 26 is also a block size of 64, so I can just subtract 1 from that. I end up with 63 as well. Now I'm going to specify my loopback address. This time I'm going to go all the way in, and I'm going to specify every single one of those bits. Alright, so there we go. So now if I do an end, show IP protocols, notice these are the networks I specified, so it's just going to match interfaces that fall within those. So here I only specified the class C. Here, because I used that wildcard, it actually shows me, you know, what those values are. Alright, so my slash 26 and my slash 32. Alright, I'm using a 90 for my internal administrative distance, which is the default. Those are my default K values that are going to specify that I'm going to use bandwidth and delay. EIGRP 10, hop count 100, and again this is just for network discovery. And that's pretty much it. I mean, I've turned summarization off. So I'm going to go ahead and exit out. We'll log out. I'm going to go ahead and configure router A, and I'll be right back. Okay, so I've configured router A. Now I'm going to go ahead and configure router C. Again, I'm specifying the same autonomous system number. No auto summary. First one I'm going to add as the classful address, and notice I built adjacencies right away because I've already configured A and B. Alright, so these are new adjacencies. These are neighbor relationships. Okay, so this next one is my users. It is a slash 28, which is a block size of 16. Alright, so 16 minus 1 is 15, so that's what I specify. Here's my my loopback address, because it's a slash 32, and end. So let's do show IP protocols. Alright, so notice same network statements that I used before. Still routing for EIGRP 10, summarization's off, same K values, all that good stuff. But notice down here, these are the two neighbors that I built using administrative distance of 90 because we're using the same autonomous system number. Alright. Show IP EIGRP question mark. I've got just a couple of entries. Some of this might be restricted because I'm using packet tracer, but we'll go ahead and we'll look at the topology table. Alright, so in this table I'm going to talk about every route to every network that I know about. Alright, there's a couple things that are important here. First off is these P's right here. Alright, you want to see P's. P's are good. A's are bad. A's mean the network, or my route to that network is unavailable at this time, and I am actively trying to find a replacement. Alright, so P's are good. P's mean some stability. A's mean something happened to the network, and I'm trying to figure out how to get back to that network. Alright, there's a thing called successor. So a successor route means that this is the best route, and I'm going to add it to my routing table. FD means the feasible distance. So when EIGRP runs its calculations, it's going to come up with a number, and the lower the number, the better the route. Okay, so in this case, if you look down here, I've got two routes to the same network, and it's going to use the lowest value. So 23065, this route. Okay, so this, because this number is less than this feasible distance, it's going to choose this as the best route to that network, and that's what will end up in our routing table. Now we can have, well, the second value is the AD, the not administrative, this is the advertised distance. So this is the feasible distance, this is the advertised distance. This value is what my neighbor told me it takes to reach that network. Okay? The difference between the two is that on this one, I'm going to go ahead and add what I know it takes to get to that neighbor on top of what it says it takes to get to that network. So the feasible distance is always going to be greater than the advertised distance, because it's going to take me a little bit to get to that neighbor, and then it takes that neighbor a little bit to get to the network. Now we can have feasible successors, and feasible successors are built from looking at this administrative or this advertised distance, and if this advertised distance is less than the current feasible distance of the route that we're using, we're going to call that a feasible successor, meaning that it's a backup route. So if this network goes, this path to that network goes down, we're going to go to the feasible successor. Okay? So that's feasible successors. All right, so let's go ahead and move on. We're going to do a show IP EIGRP, and we're going to go ahead and look at our neighbor table. All right, so these are the two neighbor relationships that we built, or adjacencies. The H is just the order in which these neighbor relationships were built. The interface is the interface that we built it on. Hold time. So here, if we keep refreshing it, so 12, 10. So if you notice, they're counting down, right? So by default, it uses, I think it's using something close to 15 seconds here. And if it's going to count down until it gets a hello from that person, right? So if it goes all the way to 0, that means we're not talking to them, and they end up getting deleted from our neighbor table. So you want to see this count down, but you never want to see it go to 0. This is our uptime, how long we've been connected to that host or to that neighbor. SRT TT is like smooth something time to transfer. I can't remember the complete acronym, but basically what it means is this is the time that it takes to go from our router to this neighbor and back. So in Packet Tracer, it's taken 40 seconds. All right. RTO, this is our time to retransmit. So if we send an update and they don't respond, we retransmit to them, right, to make sure they get it. So this is how long we're going to wait before we send that retransmission. And this is probably in like milliseconds or something like that. So it's going to wait a second before it sends that update, or it retransmits that update. Queue count is how many updates are still in our queue. So you want to always see this as 0, meaning we're sending out every update and it's getting acknowledged. If you start seeing queue count, that means we're sending out updates, but we're not getting acknowledgments back, and that's a problem, because that means there's some kind of problem with the network, and it's probably eventually going to go down, or at least that neighbor relationship. All right, so you want to always see those as 0. Sequence numbers are just for reliability. It means that, you know, this is the last update that went out. It used a sequence number of 15. So when other neighbors receive them, they can kind of make sure that they're not getting duplicate copies, you know, things of that sort. They're not missing stuff. All right, so that is the neighbor table. So if we do show IP route now, we see D's over here because this is the dual algorithm for EIGRP. All right, so if you notice, we're using 90 as the administrative distance. This is the metric or the feasible distance that EIGRP calculated. So it's going to tell us to get to that network, we're going to send it to this person using this interface. you know. All right, nothing too crazy about that one. But we'll jump out of router C, run the same command on router B, and we'll see something slightly different. Alright, so notice here, to get to the 192.168.0.8 network, I'm using administrative distance of 90, but notice I have two different routes, and they both have the same feasible distance. And that's because they're both going across the 2 meg link to get to this network. Alright, and we haven't added any delays in. So in this configuration, it should load balance between the two networks. Right? Now there's some things that you can do for load balancing and this and that. We're not going to really get into that, but I just want you to recognize that feasible distance in these two routes matches, which is why we have two routes in the routing table for it, and it's going to load balance between the two. Now if we only wanted it to do one, we could go onto one of our interfaces and add a delay on one of them. Alright, or add a delay on both of them, just add a slightly larger delay on one of them, and that would make it so that it recalculates it. It's going to get a different feasible distance value, and it's going to it's only going to end up with one route here in the routing table. Alright, now show IP EIGRP question mark. The only thing left to look at here that we haven't looked at is interface. Notice that we're using EIGRP on every one of our interfaces. We're only building relationships on the two serial interfaces, but it's probably not, we don't need to be sending updates on our loopback address or a fast ether address because nobody's connected to those. So we can do the same thing we did with RIP, is we can do config t router EIGRP 10 passive. I'm going to do passive interface default. Alright, so now I'm no longer going to send or receive EIGRP announcements on any of my interfaces. Now I'm going to go back in and do no passive serial. Now notice my holding times went down to 0 because I'm not participating anymore with sending and receiving, so my neighbor relationships crashed. But I'll do no passive interface serial 0/0 no passive I think I just went the wrong direction here. Alright, so it immediately rebuilt that relationship, and I'll do the same thing for 0/1. Rebuilt that relationship and show IP EIGRP interface. And now notice I'm only participating on 0/0/0 and 0/0/1, which is what I want. So that's pretty much it for EIGRP, or at least the basics of EIGRP. It's a great routing protocol, a lot better than RIP, but there's a little bit more involved in it, more tables, this and that. But it's going to converge faster, and it's going to work better in a larger network. It's just an all-around better protocol. But one drawback is it's Cisco proprietary. Alright, I know I probably didn't mention that at the beginning, but it's Cisco proprietary. Cisco came up with this algorithm, or this routing protocol, and so you need Cisco devices to use it. If you're not using Cisco devices, or you have somebody else's stuff in your network, we'll get into that with the next lab with OSPF. OSPF will be able to work in that kind of manner. But if you're going to have all Cisco stuff, you might as well go with EIGRP. So that's it for Lab 10. Hope you learned something. Let me know if something wasn't clear enough. Shoot me a comment, and I'll try to get back to it as soon as I can. All right, thanks.